fourth and last lecture this year on elliptic curves, and in fact the last lecture of the entire summer school. So before, we've talked about elliptic curves, we've talked about models of elliptic curves, we've talked about the torsion subgroup. Once we heard about the Mordell-Weil group, we learned how to compute torsion subgroups. So today is the day, the time has come for the rank. So let me first explain one big problem that is when we talk about points of infinite order. A big problem is to prove that points are independent. So let me show you. So this elliptic curve, this is that elliptic curve has come up before, is the Gauss curve, a so-called Gauss curve. It is the Mordell-Weil group is there's no torsion, or the torsion is trivial, and there's the rank is 3. So it is the Mordell-Weil group is generated by 3 points. For example, these 3 points generate the Mordell-Weil group. So great, that's it. But like, first question is, how do you even prove that these 3 points are Z linearly independent? Why is R not like maybe P plus Q or P minus Q or 2 times P minus 3 times Q? If you are working over a vector space, this is very easy. If these were vectors in R2, then you would immediately say this is independent. This is dependent, right? But in a Z module, where the operation of addition is this geometric construction that is very, opaque, it is very difficult to tell whether this point is linearly independent from those two. In fact, if you go to Magma, or if you go to the LMFDB, you can see that this curve has a huge amount of integral points. So one might want to know, okay, so which of all of these, which ones are generators? This is a huge amount of points. How do these all come about? I picked 3 that are very easy in terms of coordinates, but look at this very first point, -3, 0. It has to be linearly dependent on these 3. If so, then what is the linear combination that gives me that point? Anybody knows? It's crazy. Like, the arithmetic of the operation is so opaque that you can't, unless you really start doing a lot of work and doing addition, by hand. It takes a lot of work. So what is the combination? Let's find out. And it turns out that to do that, there is a theory, the theory of heights on points of an elliptic curves, heights on abelian varieties. And this is one of the main uses of heights, is that we're going to be able to answer those 2 questions, and in a very cool way. So first of all, a height on Q, if you have a rational number in lowest terms, the height of that point is going to be the log of the max of the absolute value of the numerator and denominator. That's a way to put some a height on Q that gives me some sort of like idea of the arithmetic complexity of a rational number, not just in terms of the size, but in terms of the size of the numerator and denominator. And then if I have an elliptic curve and a point over Q, then if these are the coordinates x and y, then I'm going to define what we call the naive height of that point is just going to be the height of x, which is a rational number. So take that x, put it in lowest terms, and then use the naive height on that point. Okay, that is the naive height. And that is a very nice, it gives you a lot of properties, and you can prove the Mordell theorem. So you can prove the Mordell-Weil theorem over Q. You can prove it using just this height. But it turns out that there is a better height. That one of the issues that this height has is that, for example, the height of P and the height of 2P are related, but we're going to see that with this height, we're going to get some very, very interesting relationships between the height of a point and the height of its multiples that are exact. That will be in the next slide. But in any case, the Néron-Tate canonical height it turns out to be defined as a limit. It turns out it's canonical in that a height with the properties that I'm going to discuss is essentially this height. It has to be this height, so that's why it's called canonical. And this height, so it's a limit of heights of multiples of p normalized in some way, and it turns out this limit exists, and it gives you something that is a height. But you should think just that, well, this one is, it's not far from that one. So if you want to just get an approximation of this one, what we do is actually compute naive heights first. What are the properties of the canonical height? As I said, the canonical height of m times p, of the mth multiple of p, is exactly m squared times the canonical height of p. Okay, and that is really important. The naive height has this up to a constant. So there's a constant that works for all the points. It's approximately this. So there's some small error with the naive height, that the canonical height, that error becomes 0, and you get exact formulas like this. The canonical height of a point is always non-zero. The canonical height is actually 0 even only if the point is a torsion point. Okay, that's it's not that you're going to use the canonical height to compute torsion points, but it does give you a criterion to find if a point is torsion. And of course, there's just much better ways that we've learned about how to check that something is torsion, but this is theoretically, this is very important. Also theoretically very important is that the canonical height satisfies this property, and if you are a quadratic forms buff, then you know that this has a name, and it's called the parallelogram law. And whenever you see this with a function, then you know there is some sort of quadratic form lurking in the background, and that's why one defines a pairing like this. And this pairing, the pairing of p and q, is the canonical height of p plus q minus the height of p minus the height of q. So it's the difference, or the error, in the height of p plus q versus the height of p plus the height of q. And that pairing is actually, because of this and because of the other properties, is a non-degenerate symmetric bilinear form, which is important because, well, now if I have a non-degenerate symmetric bilinear form, then I can start doing linear algebra on the points, and that's where I'm going to get my the results that I want about independence of points using that. So this is a standard construction when you have one of these pairings that is by a non-degenerate bilinear form. You construct the pairing matrix, and this is what I'm going to do. So if I have a sequence of points on my elliptic curve, 1 through n, I'm going to construct the height pairing matrix. This is sometimes called the elliptic height matrix, or I'm calling it height pairing matrix because that is the magma command. It's height pairing matrix of a sequence of points, and it returns this matrix. And it's the matrix that is, each coordinate is the pairing of pi with pj. And notice that it's going to be a symmetric matrix. And the theorem here that you want is this, that the determinant of this matrix is 0 if and only if the points that I put as input are z-linearly independent with an asterisk. Everything here is modulo torsion, because remember that torsions have height 0. All the torsion points, the canonical height is 0. So the torsion points sort of like come and go, and you have to work in just on your rational points, on your Mordell-Weil group modulo torsion. But that's okay because we can compute the torsion already, so we know what the torsion is, and now we can compute things modulo torsion to just know what the rank is. Yes?
Sorry, for the canonical height,
yeah.
Is that also an approximation to the height, or is that the most accurate height?
So the canonical height is the one you want to work with. The naive height is very easy to compute. And this is, you should think of the naive height now as an approximation of the canonical height. Okay? So when we want to have a rough estimate, then I'll look at the naive height. And then if I actually want to do computations that are going to give me something about independence, I'm going to need to use the canonical height. which is there's other formulas for the canonical height to compute it efficiently. And in Magma, in a split second, it will give you canonical heights of points. Okay, that limit looks scary, but it's actually not so scary. It's computable, and it computes very quickly with accuracy, with a very large accuracy. Okay, but this is the key, that the canonical, this height pairing matrix, the determinant, whether these vectors are linearly independent here, it actually tells me whether my points are z linearly independent up to torsion. And that's exactly what I want to get at. Yeah.
Does that property hold even for number fields?
Of this? Yes. So we do the same thing over the number field. You take your points, and then there's a canonical height over the number field. Over number fields, our heights are a little bit different. But yeah, we do exactly the same thing, and we also show linearly independence using height pairing matrix over any number field. Yes. So here's an example of this at your tax dollars at work. So here's, again, the Gauss elliptic curve. These are the points that I said were linearly, z linearly independent. Let's check that. So what I'm going to construct is the height pairing matrix for those 3 points. It looks like this. It's a 3x3 matrix. Throw it into Magma, and it gives me a matrix. I cut it off. In fact, Magma will give you, I don't know, something like 20 digits correct every time. So I cut it off to 10 digits correct, just because it wouldn't fit in my slide. And this is what it is. But it is correct. So there are algorithms to make sure that if I ask Magma to compute it to 20 digits, it computes to 20 digits, and that is 20 digits correct. And the error in the approximation is exactly that. So I can trust that now when I do the determinant of this, it's this number, and that's away from 0. So that determinant is non-zero. So these points are linearly independent. Okay? So if I have an algorithm, a provable algorithm that will compute this correct, and I know that the error in this number is is smaller than whatever, 1 to the 10 to the 10 or something, then I know this is non-zero, and then I know by the theorem that these are linearly independent. Emily, you have a question?
Yeah. It might be a dumb question, but whenever you were
No such thing.
Our points, Magna spit out like a bunch of points, like way more than the 3 that we're just dealing
Yes.
with here. Is there some sort of approach that is like quote unquote recommended, so to speak, to try and find the points that would be linearly independent, or is it just like a guess and check free for all kind of situation?
We just don't know which ones are going to be the generators. There is something though. So actually, this is a very good question. Emily was saying, okay, so look at all these points. How do I start looking for generators? What we know though is that the canonical height, for example, the canonical height grows with multiples. So if I go to these points and calculate the canonical height of all the points, I'm going to look for the points of the smallest possible height, and those should be the generators. The canonical height there's some relationship also about like linear combinations, what happens with the canonical height, but certainly among those with the smallest height, the generators are going to be there. Okay, so yes, we look, but then once you have a bunch of points that are sort of like that first row, they're all about the same height, which ones are the generators? A free Z module of rank 3 has a lot of possible generators. So many of these triplets will be generators. Okay. So which ones you pick, there is no canonical way to choose which ones are the generators, because there is no canonical basis in a generic Z3 module. Yes.
Is there a good way to even find these points in the first place? Do you just loop over a bunch of values to see what's on there, or like it's like that? Of course, if you know where the points are, you can find new points by linear combinations. But we're specifically trying to find points that aren't linear combinations of points we already found.
Right. So first of all, you can do searches. You can do there's quick ways to do searches for integral points. But then if you actually want to find all the integral points on an elliptic curve, once you actually know the Mordell-Weil group, because of height considerations, we're going to be able to show that any point beyond these is going to have rational coordinates, because the height is going to be larger, and after a certain height, the denominators are going to pop up. So you can actually do a search by height, but you need to know first generators of the Mordell-Weil group, and once you have that, then you can prove that you found all the integral points. But it's a delicate consideration. You remember we talked about Baker's bound. So actual bounds of what's the largest x-coordinate of an integral point, there's no good bounds known. They're very, very bad. So you have to come up with something else, and you do it by actually computing A, the generators of the Mordell-Weil group, B, start looking at heights, look at points up to a certain height, and then just prove that I have found all the possible combinations that had integral coordinates, and anything after that, because of heights and because of what these combinations already look like, anything else will have truly rational coordinates. Lots of questions. I really need to start moving on. Yes, Vanessa?
So I see that this formula comes as a rate of the growth of the naive height by the action of multiplying by 2. And you're dividing by 4 to the end because that's the degree of the action, I guess, but I don't see what it is. Like a 4.
Oh, yeah, I'm not sure I even have a very good answer for how, sort of like a conceptual idea of why this one is. But as I said, so you can show that this one has those properties, and then you can actually show that any height with those properties is equivalent to this one. But I don't have a good conceptual answer. What's that?
Choice of the 2 and the 4 are linked, but they could be other pairs of numbers.
The 4, if your question is about the 4, is because of this. So if I do 2p, then I know that that height is going to be m squared times that height. In the limit is going to be, if you divide by m squared both sides, then what I'm trying to get is at the height. And when you start with this one, that as I said is supposed to be close to the canonical height, when I divide by 4n, as I take the limit, I'm getting closer and closer to some value, some function that satisfies the property that I want, this property.
Yeah, okay with that. My question is how is 4 the degree of the action by multiplying by 2? Because usually when you define that dynamical height, then you have an action inside of the naive
Yes.
height, and then you divide by the degree of that action of that dynamical system. So here, if the action is multiplied by 2, how is 4?
Well, it's related to this, and it's related is the fact that h hat is a quadratic form. So if I multiply by m, then I get m squared because it is a quadratic form. So that's why if I multiply by 2, I'm going to get a 4 out, just because it is a quadratic form. Okay, let me move on. I know there were other questions. Maybe I can take one more question.
I was just confirming. In one of the slides you said determinant equal to 0 means linearly independent. Is it not equal to 0 or equal to 0? Yeah, there. Before.
This point?
No, next one. Yeah.
Oh, I'm sorry. You're totally correct. If the determinant is whoa, that's nice, but surprising. If the determinant is non-zero, then the points are linearly independent. What's happening actually? So if these, I do have a conceptual understanding of this. What's happening? Remember, I said these properties, the parallelogram law. What's happening is that I am constructing some sort of parallelogram in some n-dimensional space, and this parallelopiped that these vectors are forming, what I want to know is that this parallelepiped actually has a volume. The determinant of this matrix gives me a volume of this parallelepiped I'm constructing, and as long as that determinant is non-zero, this parallelepiped has a volume. When it's 0, the parallelepiped has collapsed in some dimension, and then it doesn't have a volume. It has maybe area or maybe a distance or something, but it's not volume, so they have to be linearly dependent. So yes, thank you. If the determinant is non-zero, then the points are linearly independent. And this is what we see here, that for these 3 points, the determinant is non-zero, and therefore these 3 are z-linearly independent. So what I'm not saying, though, with this is that they are a basis. It could be that I can take, for example, a basis, multiply all of them by 2, and that will be 3 vectors, 3 points that are z-linearly independent, but they are clearly not a z basis of this module. So once again, to prove that these are actually a basis of the Mordell-Weil group, you would actually also have to look at heights and see, okay, I have these 3, they generate something, perhaps a finite index, and then compute everything that has height less than these 3 points, and then check if any of those generate a larger module. Okay, but the question now is, what about if I take one more point? So I know that the rank is 3, so these 3 are linearly independent, and anything else has to be dependent. So how is this one a linear combination of these 3? So here's what we do. I now take the height pairing matrix for all 4 points, and this is the matrix, okay, with magma. And the determinant now, it returns that it's something up to the error, it's 0. But now, before I said my algorithm told me this determinant is like 0.4, that is non-zero, and that's provable non-zero. This, when I'm running up to the error, I cannot prove that this is 0. Okay, this is a computational problem. A very, very difficult computational problem is that computers have a very, very hard time proving that something is 0, right? So how do I use this information? I use approximate linear algebra, so numerical linear algebra, where let's assume that this is 0 and see where that takes us. So what I can do is that if this had a 0 determinant, there has to be a kernel to this matrix. And what you can prove, or one can prove, is that actually, so an extension of this theorem is that when this is 0, the kernel actually gives you a linear combination, a z-linear combination of these points that is 0 in the quotient. So a z-linear combination that is a torsion point. So the determinant gives me something about linear independence. The kernel gives me something about linearly dependence. It tells me how to compute a actual dependence of the points. So in this case, approximately, it looks like there is a kernel that is one-dimensional and is generated by this vector. What does this look like? I don't know, but this number looks like this one, this looks like 0, and this looks like the other one. So I'm going to divide. The kernel is a one-dimensional vector space. So I'm going to multiply by a vector, by a scalar, so I get integers. I'm going to divide by this number, and now I get a vector that is about 1, about 1, about 0, about 1. So it tells me that this vector looks to be the generator of the kernel. And now I can actually go to my elliptic curve and do addition, actual addition, not approximate addition, actual addition of my points. And this says that P plus Q plus T should be a torsion point. So I compute P plus Q plus T. That should be a torsion point. But when you add them up, you actually get exactly 0. And what that tells me then is that T is minus P plus Q. So I found the linear combination of P, Q, and R that gives me T. Okay? So there's a problem in the book I forget the number, but there's a problem in the book with some elliptic curve and a bunch of rational points, and the question is find generators of the Mordell-Weil group. And what you can do is to start playing with this. You start with, well, 1, is it of infinite order? I can start with that one for now. Take a second point. Is it of infinite order? Then use this kind of thing to see if it's a multiple of each other. Are they independent? Go to the next one, and then try to grow that set into a generating set. Yep.
How do we know P plus Q plus 2 P is 0? Do we just, like, is it computation?
I haven't proved that, but that is actually from the properties of the height matrix. You can actually show, this is I think some exercise also in the book. You can show that from the properties we know about the height, the canonical height, and the fact that the height pairing is a non-degenerate bilinear form, you can prove that if the determinant is 0, if you have something in the kernel, then that gives you a relation among the points. Okay? I didn't mean to draw it. So that's something you can prove. I haven't proved it here, but the kernel, actual vectors with integer coefficients in the kernel, they actually give you algebraic relations between the points. And that's how we prove independence, how we find dependencies. More things about the rank. So the rank, actually, it's very difficult to compute the rank of an elliptic curve, but the good news, one piece of good news, is that there are actual bounds. So if you give me an elliptic curve, I can fairly quickly come up with a bound and tell you the rank is at most 10, or I can give you a bound for the rank. And sometimes that bound is sharp, and then we're done. So for example, this is just a sample bound that is easy to state, is that if you have an elliptic curve over Q, and your elliptic curve is given by this kind of Weierstrass model, notice that there's an x squared there, so it's not a short Weierstrass. It's a long Weierstrass model, but just of this sort. You can replace this by any elliptic curve that has 1 2-torsion point defined over Q. This is what these models parameterize. So as long as you have 1 2-torsion point defined over Q, then the rank of that elliptic curve is given by, or is bounded by, this formula, where nu is an arithmetic function that is the number of distinct prime divisors of this number. For example, if you have this elliptic curve, remember this actually came up as one of the examples that I used, that are there 3 consecutive integers or 3 consecutive rational numbers whose product is a square. That's what this Diophantine equation parameterizes. And that Diophantine equation, well, it looks like this, the polynomial in x. So I can take, okay, what is this? That will be 9 minus 8 is 1. How many prime divisors are there of 1? 0. Nu of 2, how many prime divisors are there of 2? 1. So this is 1 plus 1 minus 1. That is not 0, is it? No, this is 0 plus 1 minus 1. That is 0. So the rank is less or equal to 0. So the rank is 0. So now I know that the rank is 0. So I just have to compute the torsion subgroup of this to figure out all the possibilities. And the torsion subgroup of this is actually just all the ones with y equals 0. So the only possibilities for rational numbers that are consecutive, or x plus 1, x plus 2 rational, whose product is a square, are only those combinations that involve 0. So minus 1, 0, 1, 0, 1, 2, those are the solutions. Great. Now, what else can we do to try to tackle the rank, to actually compute the rank itself? We have analytic methods, which are conjectural. We have the BSD, the Birch and Swinnerton-Dyer conjecture. So that involves computing a Hasse-Weil L function. So how do you compute an L function of an elliptic curve? The L function is defined as an Euler product, and for each prime, there is a factor on this infinite product, And each factor is defined as follows. It depends on the reduction of the elliptic curve. We know that the bad primes divide the discriminant of my elliptic curve, so there's only finitely many bad primes. So for almost all the primes are of good reduction, and for those, the L factor, the L polynomial, where I'm going to plug p to the minus s for t, is this polynomial, where AP is what we call the trace of Frobenius, and it is actually the error in Hasse's bound. Remember, Hasse told me that over Fp, there should be about p plus 1 points, and if you compute the error, it turns out that is the key number here as a coefficient in this polynomial that goes in here, in there. This might seem like, what the heck is this about? Like, how do you know this works? Where is this coming from? Because of cohomology. Okay, so there is an explanation of how to come up with these terms, in one cohomological way, and the action of Galois and things like that. So anyway, there is a description, a recipe to come up with these Euler factors. The case of bad multiplicative reduction, remember that there were several types of reduction types. When we have multiplicative reduction, the L factor is 1 minus t or 1 plus t, depending on whether we have a split or non-split multiplicative reduction. And you can go back a few lectures to see what that meant. And then finally, if the reduction is bad additive, then the L factor is just a 1. It doesn't contribute anything to the L function. Okay, so we can build an L function and compute values. And what the Birch-Swinnerton-Dyer conjecture says, I wish I had more time to discuss how this came about. This is the sort of like the modern formulation of the Birch-Swinnerton-Dyer conjecture. The Birch-Swinnerton-Dyer conjecture, like what they actually were doing when they came up with the conjecture was something very, very was smart, but it's a posteriori, of course, it's a very simple idea. They wanted to check, can I use the number of points over Fp? Remember that I told you that finite fields would have consequences about torsion, consequences about rank. What they said is, like, can I see the rank on the number of points over Fp? If the rank is high, there should be a lot of points defined over Fp also, right? So I would imagine that if the rank is high, these numbers must be high, which means that this error is lopsided and it's negative a lot of the times, okay? And they were trying to quantify that. Can I see that the elliptic curve of rank 5 has these lopsided? And then they put them all together as a product. They were looking at, okay, how about we do a product of the number of the points over Fp divided by p plus 1, something like that. Yeah, hold on. It's like, so what, dividing plus 1, once p is large enough, like when you are like waving your hands doing infinite series, it's not much of a difference. So I'm going to put a p. And then you can check that what happens if you replace AP by this formula, it sort of becomes this thing when s equals 1, it becomes sort of this product, which is what Birch and Swinnerton-Dyer were looking at to try to estimate how rank affects the totality of the number of points over Fp. So anyway, this is the modern formulation, is that the L function, so that growth at s equals 1 of their product, when you invert it, they would give you a zero of a certain, a zero of a certain multiplicity. And what the BSD conjecture nowadays says is that the L function can be written, the Taylor series at s equals 1 starts like this, which means that at s equals 1, there is a zero of this order, and the order of the zero is the algebraic rank of the elliptic curve. The order of the zero at s equals 1 is the algebraic rank. That's the first part of BSD. The more complicated part is that the residue, this number, this coefficient, the first coefficient in the L series, just like if you've seen the class number formulas and other formulas involving special values of some other L functions, of the Dedekind zeta function, of the Riemann zeta function, there is information that are hidden at poles. It turns out that that value, it's a formula, I'm not going to write it here, but it's a formula that is like explicit, and it depends on all these fine invariants of the elliptic curve, one of which we just saw today. So if you have an elliptic curve, the rank is 3, you have 3 generators, and we did this, remember, for this elliptic curve, I computed this number appears in the L function at s equals 1, and because this volume of that parallelopiped spanned by these 3 generators of the Mordell-Weil group, this volume is what we call a regulator, and it comes up when you prove, for example, the Dirichlet's theorem on the structure of the unit group. There is a regulator. When you look in here, there is another regulator, this volume. This volume appears as one of the factors, one of the more complicated factors, in fact, of the residue at s equals 1 for the L function. So it's one of the factors that appear in the formula. The size of the torsion subgroup appears there, and other very fine invariants of the elliptic curve appear there. Okay, so let me show you an example again with the Gauss elliptic curve. With magma, you can define the L series, so L is the L series of that elliptic curve, and then you can evaluate that L series at values. So because the rank, I know the rank is 3, I can do it computationally. I can, by the way, these numbers, when it returns 0 like this for the L series evaluated at 1, there is a 0 because provably we can compute enough coefficients of the L series to compute this to that precision. So it is 0, but to this precision. Again, this is a very good indication that the L value is 0. It doesn't prove that it's 0. That's a very difficult problem again, and this is where Gross-Zagier came in, and there is some other theoretical formula to compute values of L series to actually prove that something is 0. I believe to this day we have not seen a proof of any L function vanishing to order higher than 4, right? Yeah, so there's no paper out there that proves this L function vanishes to order 4 anywhere. Okay, so the Gross-Zagier formula we were able to use that, and this is actually where this elliptic curve came from, to prove that something vanishes to a higher order, but order 3. And this is what we can see is that the derivative of the L series, the first derivative looks like it vanishes to that error. The second derivative looks like it vanishes. The third derivative, it is definitely not vanishing. Okay, so the rank is, analytically, this looks like the rank is 3, and it's definitely not 4. Great. What about algebraic methods? So to actually prove things algebraically, sorry, that's it for analytic number theory. Somebody was, like hoping for more analytic number theory. That's at least in my course, as much analytic number theory as there's going to be. So for algebraic methods, we have what we call the methods of descent. There's a very rich theory nowadays of descent methods. There's all sorts of flavors and varieties of descent methods. What I'm going to explain here is sort of like the simplest method that we know. It's called complete to descent. And in the complete to descent, to make it work, at least so I don't have to leave the comfort of Q, you start with an elliptic curve that all the 2 torsion points are defined over Q. Okay, so I'm going to write, I'm not going to use my my paintbrush again. So we're going to assume that those coefficients, those roots, are integers and they are different from each other, so it's a smooth elliptic curve. And this implies that all the two torsion points are defined over Q. And then for that elliptic curve, I'm going to try to see if I can find the rank of elliptic curves in this family. And so where would the points be? If I'm going to try to motivate how descent comes about, where would the points be? Suppose I have a rational point on this elliptic curve, then it satisfies the Weierstrass equation, right? And if this is true, well, the product is a square, so this must be almost a square, almost a square, almost a square, enough that the product of these almost not a square has to be a square. So you can write this as almost a square, almost a square, almost a square, and then the product of these ABCs has to be a square. And in fact, is the square written like so. Okay? So I haven't done much in here except that maybe I can try to solve this equation or these 4 equations. If I could solve that, then I'm done. Let me show you that this actually happens on elliptic curves. I can write points in this way. So for example, here's an elliptic curve with full 2 torsion. This is a point on the elliptic curve that is not a torsion point. This is a point. This is a point. The addition is a point on the elliptic curve. And that deconstruction of the fact that this is a solution, if I take this point minus E1, E2, and E3, it is a square times something, a square times something, a square times something. And then you can see that this triple, minus 14 times minus 7 times 2, is a square. Okay, and that's why that point is a point. How about for Q? For Q, you do the same thing, and it is also that you have that decomposition, and then 2 times 1 times 2, it is a square. Okay? Where am I going with this? Where I'm going is like, let's see what happens to S. So this is, again, what happened to P and Q. This is what happens to S. When I do that decomposition of these factors, I get a square times something, a square times something, and something times a square. So I get minus 7, 1. This is what I get for P. This is the triple ABC. This is for Q, the triple ABC. And this is the triple for S. Can you tell me if there's a relationship between this column and these columns? Okay, so P divided by Q equals S, multiply it together gives S. So let's see, minus 14 times 2, that's minus 28. That is not right.
2 of them 3 points.
What's that?
2 of them multiply to give another one of them, not necessarily.
Oh, not necessarily. You pick and choose. You're saying like 2 times minus 7 is minus 14. Minus 7 times 1 is this one. And here, which ones did you pick here?
2 and 1.
Oh, 2 and 1 is 2.
I mean, Q times S is P.
Any 2 of them were multiplied to be just
Or ultimately P over Q is S.
Okay, so at least you got it right that there's some multiplicativity connection here. And the connection is that minus 14 times 2 is minus 28. But you see, how did we define A, B, and C? A, B, and C were numbers up to squares. I took the square-free part of my numbers. That's how I came up with this, or with this really, is that this was like 16 times minus 7, and then I found the square-free part of that number to come up with B. So A, B, and C to begin with are defined up to squares. So minus 14 times 2 is minus 28, minus 7 is minus 28 modulo squares. Minus 7 times 1 is minus 7 modulo squares, it's also equal. And 2 times 2 is 4, is 1 up to squares. And that's the key, that's the connection that somehow S, or this triple, remembers the group law between P and Q, that P plus Q is S. Somehow there's a group law on these triplets of square-free parts of these numbers. And you can actually prove that that is true, that there is such a thing, and we can put it in like our fancy language, that if I have an elliptic curve of that form, there is not just a map, but a group homomorphism. That's really important, from points to triplets of numbers, triples of numbers modulo squares, which is exactly what I said, except, so for most of them, if the y-coordinate is non-zero, is the triple we just talked about, is x minus e1 modulo squares and so on. And then for the points of torsion, there is just a different formula. But I can come up with what the formula is, and it gives me a group homomorphism. So I can, instead of talking, remember how difficult it is to talk about addition on the elliptic curve, I can now throw them all into this group where the multiplication and the group operation is very simple to understand. Okay, so that is one step. And moreover, so if delta p, if the image of a if the image of a point is delta 1, delta 2, delta 3, it turns out that the 3 multiplied to 1. Okay, that is maybe not, it wasn't so obvious. Well, yes, we said that a times b times c was a square, so it has to be the trivial class modulo squares. And the kernel of that map, the kernel of this map, it turns out to be exactly twice the torsion point. So any torsion point, twice the rational point. So any rational point that is twice a rational point is in the kernel, and that is exactly the kernel. This gives me a lot of information. Let me say first, with an elliptic curve, how that comes about. So you have this elliptic curve is actually z mod 2 cross z mod 2, so torsion subgroup, and then rank 2 generated by those two elements. I can compute the images through delta of those elements, and then the image through delta will be generated by these 4 triples. Okay? But what I wanted to show you is that actually the things that are the divisors of all these numbers turns out to be bad primes for the elliptic curve. So the elliptic curve, it turns out it has bad reduction. You see this is 46, that's 23 times 2. There's bad reduction of 23, there's bad reduction of 7 and 2. So it turns out that these values that appear dividing these numbers, the factors, have to do with the bad reduction. And that allows me to actually, one thing is like, okay, I know an elliptic curve, I know the Mordell-Weil group, I can figure out what the image is. But what I want is, not knowing the Mordell-Weil group, try to compute the Mordell-Weil group. And it turns out that you can show that, so one big problem also of this map is that this is very, very infinite. Okay, so if I'm trying to figure out, okay, what is the image here, just so I can compute what this is infinite, so how I have to cut it down to something that is finite. And this proposition tells you that if something is in the image, then there are representatives, modulo square, that are integers, and they are actually divisors of this triple product, which is related to the discriminant. So it's primes of bad reduction. Okay, they have to be primes of bad reduction. And that tells me then, because the kernel was 2 times EQ, that delta gives me an injection into something that is finite. And finite there means a bound. So right away, because I can compute this, I can compute the number of primes of bad reduction, I can compute how many elements, how many triples there might be in here, I can compute exactly what this gamma is, and I already have some progress, which is I can come up with a bound for the rank just by computing this gamma. And now the question is, how do I know if something is actually in the image? Once I have an element in gamma, a triple, delta 1, delta 2, delta 3, how do I know if it actually comes from a rational point of infinite order? So here it is. Moreover, this happens, that if something is in the image, then it is a solution of this equation that we had before. This doesn't look very, it doesn't simplify anything. However, you can manipulate this to have less variables, and it has to be, if it is a solution of this, it is a solution of something like this. Remember that the EIs are given, the deltas are given. If I want to show, is this a point? is this something in the image? So everything in here except x, y, and z is known. So I have to solve this. I have to figure out if there are points in this space. This is what we call a homogeneous space. And this, in the very first lecture at the end, I had this image of a descent that I started with an elliptic curve. I had like what I call Selmer elements. These are the things that are going to become Selmer elements. So basically what I have to do to try to find rational points, I have to figure out if these spaces have points. And what we do is use p-adic methods on those spaces because these are two, it's a pair of two quadratic equations. Together, it is not quadratic. But if I look at one equation at a time, I have Hasse-Minkowski for each one of the equations. So I can try to figure out, are there real points on this? No real points? Forget it. There is no rational point on that space. I can throw it away. If there are QP points for all QPs and the reals, and there are QP points on all reals for each one of them, then I call a Selmer point, and there is a possibility. It looks like there should be a rational point, at least from the point of view of Hasse-Minkowski for quadratics. So what we do is through that map delta, this would be now, this is a subgroup, even smaller, of gamma, of that gamma that we had before. And what we do is look at all those spaces that are what we call locally solvable everywhere spaces. And those are the candidates for rational points. And then the problem is, why is this method sometimes doesn't work, is that there are some of these spaces that are locally solvable everywhere. So there are QP points for every P, but there is no rational points. And that's the difficulty of trying to figure out whether what's the image of that map delta is in here. That's what's called the Tate-Shafarevich group. And you can realize it as these type of homogeneous spaces that are troublesome. So let me just end with a picture of what happens for the fruits Diophantine equation, which, by the way, it is in the LMFDB. I was very surprised that it's there, so maybe I can try to convince something at the LMFDB to put it as one of the interesting curves, to call it the fruits Diophantine equation, or the fruits elliptic curve. And for this elliptic curve, what happens is that if you try to do a descent, in this one there is a point of order 2, so you can actually do you can't do the complete descent that I just taught you, but you can do something called a 2-isogeny descent. In any case, you can compute the 2-Selmer group, and you can compute that the 2-Selmer group actually is Z modulo 2 cross Z modulo 2. And by looking at the spaces, the homogeneous spaces that I told you, you can figure out that one of these spaces that generate this group of order 4, one of the spaces corresponds to a 2 torsion point, and the other space corresponds to a generator of infinite order, which is easy to find because it was like 8, minus 8. So it was easy to find. So what turns out then is that in this particular curve, SHA is, or the 2 part of SHA is trivial, so there is no problem with the local to global principle on the homogeneous spaces, and I can complete the descent and prove that the rank is exactly 1 for the fruits Diophantine equation. So I think I'll stop there. Thank you.